Hello, in this video we're going to talk about least square solutions. So when we have a system of linear equations like ax equals b, we know that we can have one of three outcomes: unique solution, infinitely many solutions, or no solution. In practice, we often run into this case of no solution, and let me give you an example of what I mean here. Suppose we have a bunch of data points here. We've gone out into the real world. We've collected data. And what we want to do is we want to fit a linear model to this data. And if we put a line through the data, there is no linear model that's going to drive through every point. And so the idea here is we want a linear model, but no solution exists. And rather than just give up on the problem here, what we do is we use some techniques from least squares. We find a least square solution. Okay, so that's what we're going to talk about in this video. So before we proceed further, I'd like to give you a few definitions. The first definition is for an overdetermined system. So definition: a system is called overdetermined if it has more equations than variables. Okay, and here's an example of an overdetermined system. Suppose we had x plus y equals 6, negative x plus y equals 3. Two x plus 3 equals 9. And we can put that in the form ax equals b. So here's our coefficient matrix. We have a 1, 1, negative 1, 1, and a 2, 3. Here's our vector x, xy, and our vector b consists of the constants 6, 3, 9. Okay, so the idea here is that this is an overdetermined system, right? Because we have more rows. We have 3 rows and 2 columns. Okay, so our old approach for solving systems of linear equations, we could either put this in an augmented matrix, and we could use techniques RREF. That's certainly an approach we could do. We've also talked about the inverse, and so you could multiply on the left by A inverse. So you have A inverse AX equals A inverse B. And that's a great approach, but it's only a great approach when A inverse exists, right? A inverse might not always exist. So let's make a note of this. So the big but here is that A inverse might not exist. And we've seen one case of that in the overdetermined system, right? So one scenario, and there are other scenarios, but one scenario where this A inverse might not exist is if you have an overdetermined system. And the picture for this overdetermined system from our previous slide looked like a bunch of data points all over the place here, and we're trying to fit a linear model to this data, and we realize there is no linear model that drives through all the points. It's overdetermined. Okay, so our new approach that we're going to use, instead of multiplying on the left by this thing called the inverse, we're going to use the pseudo inverse. So when A inverse does not exist, we can use the pseudo inverse. Let me spell that right. I'm about to make a typo there, but we'll correct that. The pseudo inverse. Okay, let me define what is the pseudo inverse right now, and then we will use it. So, definition, the pseudo inverse is the pseudo inverse of a matrix A is given by the following, and I'm going to use the notation P inverse or PINV. That's the MATLAB code for pseudo inverse. The pseudo inverse, you could compute it by hand as well. It is the inverse of A transpose A times A transpose. And again, the MATLAB command for this, which we will see in a future video, is P inverse of A. And in general, you don't want to get involved in computing these things by hand. It would take a long time. You should use technology to your advantage here.